So let's start chapter 6. Now, in chapter 5, we dealt with binomial distributions, and we dealt with distributions, probability distributions, that just had a discrete random variable, which meant that we could only have a certain number of items, a finite number of values that would occur, or a fixed number, or a countable number. So something that wasn't infinite, or that you could count. In chapter 6, we deal with something different. Chapter 6 now, we're going to study continuous random variables. Those are those ones that could take on an infinite number of possible values. So it wasn't just like rolling a die where you could only get 6 possible outcomes, or pulling out a card where you only get a fixed number of outcomes. Here we can study any number of outcomes, an infinite number, such as like when you're measuring something. And we've talked about this several times, but if you're measuring a length, you're not just going to measure something that's 11 inches or 12 inches or 13 inches. You could be anywhere in that span, right? You can get as precise as what your measuring tool allows. So it's not like you can count measurements. They're not in any particular order. What's the next number after 3.01? You go, well, I don't know. It's not 3.02. You can do 3.01000001. That's in between there somewhere, and you can't count that. So that's what we're studying here is a continuous random variable. First thing, before we actually get on into continuous random variables, I got to tell you that if the continuous random variable has a symmetric bell-shaped curve, do you remember what the symmetric bell-shaped curve was called when we had something like this? Say it again?
Normal distribution.
Called it normal, that's exactly right. So if we have a normal distribution or a bell-shaped curve, that's really what we're looking for in our chapter 6, is something that's normally distributed. If we don't have a normal distribution, none of this stuff really applies. So what we need out of this section, out of this chapter, is for our continuous random variable to have a symmetric bell-shaped curve, otherwise known as a normal distribution. Continuous random variable. Our continuous random variable has a symmetric bell-shaped curve. It's considered to have a normal distribution, or be normally distributed. And that's what we're looking to have happen. In section 6.2, what we're going to be looking at is something called the standard normal distribution. Now, I'm going to introduce this concept of a distribution with continuous random variables in just a little while. And I'll kind of build from what's called a uniform distribution to a standard normal distribution, so you can kind of see the differences and understand what we're going to be doing. Basically, here's our idea. You remember the whole z-score idea, right? I hope so. If you don't remember the formula for z-score, no problem, I'll give it to you in a little bit. But what we're going to be doing is combine the idea of the area under a curve, which if you've had calculus, you know that you can find the area under a curve. Now, this is not calculus-based statistics, but you could do calculus-based statistics. There is such a class, which sounds awesome, right? For those of you, I don't know how many people have had calculus in here? Oh, almost all my students. You didn't have the opportunity to take me. I'm sorry for you. But that's, the rest of you, yes, fantastic. If you're interested in calculus, I teach next semester. Isn't it a good class? Just lie. Anyway, what we're going to be doing is we're going to combine the ideas of area under a curve with that of a z-score and probability to tie all this stuff together. That's the goal. The idea of area as being a probability combined with our z-score. And what we need to realize is that the areas ultimately under a curve are going to represent probabilities for us. So we're going to tie those concepts together and be able to figure out probability simply from a z-score and the fact that we have a normal distribution. So this is a really big idea for us, that we are dealing with a normal distribution. If we don't, if we have a skewed distribution, it's not going to happen for us. We need something that's symmetric for this to work. Now, before we get on into a normal distribution and a standard normal distribution, which is where we're headed, what we need to talk about first is a uniform distribution, because I want to get the idea of area combined with probability to kind of fit in your head. What's uniform mean, by the way? What now? What's uniform mean? That thing you put on when you go into the military. It's a uniform. Why is it called a uniform?
All of them are identical.
That's right. Everything would be the same, right? Uniform means the same. So in a uniform distribution, all the outcomes are exactly the same. So if you look at the distribution, it would just have a flat line. It wouldn't go up, it wouldn't go down, it would just be the same all the way across. You with me on that? It's the most basic type of distribution that we can have. So all the values would have the same probability of occurring if we were looking at a uniform probability distribution. So all values have the same probability of occurring.